The topic of this section is non-equilibrium applications of Newton's laws of motion. The difference between equilibrium and non-equilibrium conditions in regard to the effects of forces on the motion of an object has to do with whether or not the object is accelerating. When the acceleration of an object is zero, the object is in equilibrium. When the acceleration of an object is not zero, the object is not in equilibrium. In the case of equilibrium, we apply Newton's second law and say that the sum of the forces, and therefore the sum of the x and y components of the forces, are equal to zero. Under non-equilibrium conditions, we also apply Newton's second law, but the sum of the forces is not equal to zero. In this case, the sum of the forces is equal to the mass times the acceleration of the object. The sum of the x and y components are also equal to the mass times the corresponding components of the acceleration. When solving non-equilibrium problems, we use the same reasoning strategy as for equilibrium problems, except in the application of Newton's second law, where the sums of the forces are now not set equal to zero. The steps are the following. 1. Choose the object on which the forces act. 2. Draw the free body diagram showing all of the forces. 3. Choose a convenient set of axes and then resolve all of the forces or project them onto the chosen axes. 4. Apply Newton's second law for the sums of the components and set the sums equal to the mass times the appropriate component of the acceleration. 5. Solve the equations obtained in step 4 for the unknowns in the problem. Let's do an example of a non-equilibrium problem. Consider a block of mass m on an inclined plane of angle theta. There's kinetic friction between the block and the plane, but the block accelerates down the plane. Now we just apply the steps. 1. We identify the object as the block. Next is the free body diagram. There are three forces: the weight W acting vertically downward, the normal force N acting perpendicular to the plane, and the frictional force F sub F acting parallel to the plane. We now choose the axes. The most convenient for this problem are with the y-axis perpendicular to the plane and the positive x-axis down and parallel to the plane. The only vector to resolve in this case is the weight. 4. We now apply Newton's second law for each component. The sum of the forces in the x direction are equal to Wx minus Ff, which is equal to m times ax. The sum of the forces in the y direction equal n minus wy, which is equal to 0 since the object cannot accelerate perpendicular to the plane's surface. Finally, we could solve these two equations for the specific unknowns of the problem. You will have to analyze problems in this manner well beyond this chapter. Later, you will learn about numerous other forces, such as electric forces, magnetic forces, buoyant forces, and so on. Problems involving those new kinds of forces will also require the application of Newton's second law in equilibrium and non-equilibrium conditions. The important concepts of this section are the following. First, Newton's laws apply to both equilibrium as well as non-equilibrium situations. Second, to solve non-equilibrium problems, apply the same steps for solving equilibrium problems, except the sums of the forces are equal to the mass times the acceleration rather than 0 for each component.